What up, what up? Today in AP Precalculus land, we are going to talk about the first four sections of Unit 2. Lots of exponential stuff, growth, decay, moving it, just like the animals from Madagascar like to do. They like to do that, you know. They like to move it. Just get right into it. The first section really talks about stuff you probably learned in Algebra 2, maybe even Algebra 1, and that's arithmetic and geometric sequences. Now, an arithmetic sequence is basically you add or subtract the same number to get from one number to the next, like 2, and then 5, and then 8. And you're like, oh, it looks like all you're doing is adding 3. Arithmetic sequence. A geometric sequence is when you take a number and multiply it from one term to get to the next, and that term is used over and over and over again. And so you would look at this problem and say, oh, it looks like you're multiplying 2 every single time. That's a geometric sequence. The number you add is called the common difference. We'll get to that in a second. The number you multiply is called the common ratio. We'll get to that in a second. What we need to do is make sure we feel comfortable about the equations for each one. So the arithmetic sequence equation is given to you by a sub n, which represents the nth term of a sequence. So if I'm like the 18th term in an arithmetic sequence, you would say a sub 18. That's going to equal the first term, a sub 1 is the first term, plus n. So remember I said the 18th term, n is 18, minus 1 times that common difference, that number that you add to get to the next number every time. That is the equation for an arithmetic sequence. Again, okay, you were the nth term, right? You were the first term. N has to do with the term that you're dealing with. And D is the common difference, what you add to get from one number to the next. Then you have the geometric sequence equation, which I'll write down here to give myself a little bit more space. Slightly different, but a lot different. A sub n, again, you know, the nth term, that hasn't changed. That's going to equal the first term, again, so far that really hasn't changed, easy to remember, times the common ratio to the n minus 1 power. So the new thing here is the fact that now it's multiplied, your first term is, to the common thing that you're dealing with. And again, we said R was common ratio. So I'm going to whip out some of these equations every now and then during this packet problem thing. Yeah, that's not going to go away anytime soon. Okay? All right. That takes us to exponential functions. Now, what an exponential function, generally speaking, looks like is going to look exactly like the geometric sequence. F of x is going to equal a, which is like your first term, times b, which is like your common ratio, to the x power. It's just the difference between this guy in exponential functions and geometric sequences is we're not subtracting 1 here. Now, we're going to do a little bit of manipulation later in this video. You'll see what I mean, but that is the exponential function. Exponential functions will look something like this, or something like this, where what you're going to have is you're going to have a graph that starts out and then explodes, or it just kind of levels itself out. Very similar to some of the rational stuff that we saw in the previous chapter. Now, what do A and B stand for? A just basically represents what your picture is going to look like as far as stretching or shrinking. What's very, very, very important is the B. If B is greater than 1, not equal to, just greater than 1, you have what's called exponential growth. Okay, so maybe you start out with 2 objects, and then you have 4, and then you have 8, and then you have 16. And what I'm doing is I'm multiplying by 2 every time. So in the case that I just made up, B is 2, which is greater than 1, which is exponential growth. Now I'm going to be very, very, very careful how I word this, because you're probably thinking, well, what happens when B is less than 1? B has to be in between 0 and 1. If B was negative, the whole thing goes haywire, because then all of a sudden you're saying a negative to an exponent, and then a negative to an exponent, which means you're going up and down and up and down and up and down, because if you square a negative, it becomes positive. And if you cube a negative, it becomes negative. And if you quadruple a fourth a negative, it becomes positive, and so you're going everywhere. So I'm not just going to say less than 1. I'm going to say between 0 and 1. That is what's called exponential decay, if I knew how to spell. Over there is what it would look like. So if I had like a car and my car started out at like, I don't know, let me be realistic, $100,000, I bought it used. And then like the next year it was $50,000. And then the next year was $25,000. I'm taking half every time, which means it starts way up here and then cuts in half and then cuts in half and then cuts in half and starts to level itself out towards like a horizontal asymptote of some kind. So very similar to the rational function stuff that we saw in the previous unit, but not the same. You know, there are connections. Really? I'm just going to get right into it. I guess one of the things that I didn't talk about, let me go back, is what if I want to move one of these things? Like what if I want to take something that looks like that and maybe shift it up or shift it left or something like that? Let me rewrite this whole thing and add some fun facts to it before I go and do a bunch of examples. If I were to take a number in front of the A and make it positive or negative, it determines whether it looks like that or it looks like that. It just simply flips it upside down. Okay, same thing with that way. So a positive A may look like that. A negative A may look like that. Okay, B is just going to be B. We're not going to go inside the B. Now, you might be thinking, hold on. Whenever we wanted to move left or right, didn't we go inside the X parentheses? We did. That's not X. That's B. Big difference. If I wanted to move this guy left or right, I'm going to subtract or add from the X. And what we have to be careful here, okay, what we have to be careful is, well, let me write out the whole thing. All right. So let's look at the H and the K first, and then we'll go back and talk about the A, even though I kind of brought it up just a second ago. If I wanted to move right, okay, if I wanted to move right, it's going to be a positive H. Okay, so like X minus 5. You might think, oh, minus 5? Don't we move left? No, a minus 5 implies the opposite of this. We're moving right. So if you have X minus 5, move right 5. X minus 10, move right 10. However, if you have X double negative, which is plus 10, you are going to move left. Okay. We know with the K's, if a number is floating around on the outside, that kind of acts as a y-intercept or something along those lines. Okay, a positive K just means you move up, and a negative K just means you move down. What the A does, and I forgot to talk about that earlier, is it takes your number and it either stretches it or shrinks it. A smaller A has you shrink it. A larger A has you stretch it. So this has to do with the horizontal stretch. Okay. I don't think we're going to see that a whole ton because usually we're going to be given numbers and we'll take it from there. So we're going to start right off the bat. I don't think I have any calculator problems until the end. I think I just saved them for last so I don't have to move my face a bunch of times and check because that's the moneymaker. Come on. Find the common difference. What am I doing to get from, well, first off, it is arithmetic. So yes, it tells us that. The common difference is what I multiply or subtract or add, what I add to get from one number to the next. And it looks like this is negative increasing, so I'm going to add 1.25 every time, plus 1.25, plus 1.25. I'm confident in my answer. So what's the common difference? D equals positive 1.25. If our number was going down, it would be negative something. The common difference is what you always add to get from one number to the next. So if I wanted to find the next three terms, I'm going to add 1.25. So negative 5 plus 1.25 is going to be 0.75. And then add 1.25 to that is going to be 2. And then add 1.25 to that is going to be 3.25. Find the explicit formula for the sequence. And if you're like, explicit formula? Is that a formula that involves more cursing? Yes. Which, if you have children in the room, have them leave because I'm about to use a curse word. I'm just joking. I wouldn't do that. but I did warn you. The explicit formula is what we wrote down on the last slide. A sub n equals a sub 1 plus n minus 1 times d. Okay, let's label everything that we know. All right, we already know that u are d, God is good. We know that u are the first term, so I'm going to call you a sub 1. What else do I know? That's just about it. So the general formula for the explicit formula is going to be a sub n equals the first term, negative 4.25 plus n, which is, I don't know, minus 1 times d, which is 1.25. Okay. Now, you might look at problem D here and say, oh, let me get my calculator. Now, we don't need a calculator. We might want a calculator, but we don't need a calculator. So in order to find the 88th term, n is now 88. So I'm going to use this guy right here and say a sub 88 is going to equal the first term, negative 4.25 plus 88 minus 1 times 1.25. In other words, negative 4.25 plus 88 or 87 times 1.25. So let's just do the old-fashioned way. I have all this space up here. Let's try to find out what 87 times 1.25 is. Okay, I never said it would be pretty. I just said it would be fun. All right, old-fashioned way. We have, that's 35, 43, carry the 3, blah, blah, blah. Put a 0 there. That's 14, that's 17, 2 zeros, and then 87. So you're going to add those up to 5, 7, 8, 9, and put a dot here. I hope I did that right. I mean, that seems kind of promising. I mean, a quarter of 88 would be 22, the Taylor Swift special. So you would add almost 22 on top of that. So yeah, I like it. So we have negative 4.25 plus 98.75. So working backwards, 98.75 minus 4.25 is going to be 94.5. If I made a mistake on that, which is possible, I do make mistakes from time to time, leave a comment in the chat. It happens where people say, you made a mistake, and then I cry for hours. Oh, I wish I could say I was joking. Next one. We've got ourselves someone spilled ooze on their calculator. What were these, Ninja Turtles using math stuff? While making an equation for geometric sequence. All right, so let's remind ourselves that the geometric sequence is a sub n equals a sub 1, the first term, times the common ratio times n minus 1. For those of you wondering, am I going to have to memorize these formulas for the AP exam? Yes, memorize them. Memorize them good. All right, so find the output values when the input values are 0, 3, and 4. Oh, that ooze really got in the way. Well, let's see what it looks like we're doing. We know it's geometric, so I know that no matter what, I multiply the same exact numbers every time to get to the next guy. What do I multiply to negative 16 to get to negative 8? A half. So when you have 0, 0 is going to be a half of negative 8, which is negative 4. A half of negative 4 is negative 2. A half of negative 2 is negative 1. A half of negative 1, is that what I want to do, 3 and 4? Yep, a half of negative 1 is going to be negative half. And then a half of a half is going to be negative 0.25. A quarter, that's supposed to be 0.25. So let me write that out here. Negative 4, negative 0.5, and negative 0.25. were the three numbers that I was supposed to come up with. Find the equation for the geometric sequence. All right, be careful. The first term in this guy is not negative 18. The first term is when n is 1. And when n is 1, we have negative 2. So negative 2 is a sub 1. Be careful. We already said that our ratio was a half. So let me write that up here. Our common ratio is what I multiply from one number to get to the next. And that's a half. And that's really all the information I need. A sub n equals the first term, which was negative 2, times r, which was a half. So I like to wrap that in parentheses, even though it may not be necessary. So that dot's not really necessary. It's all good. To the n minus 1. Okay. Find when x is 6. So in this case, x is 6 implies n is 6. So what I need is I need the sixth term, which I don't have. And I'm not going to keep this process going on any further. I'm going to try to do this using the formula that I just came up with. So a sub 6 is going to equal negative 2 times 1/2 to the 6 minus 1 power. And the 6 minus 1 power is the same as the fifth power. Now, for me, with problems like this, I prefer to deal with fractions. You know, a lot of you might be like, let's do decimals and let's just keep the pattern going. No, because for whatever reason, dividing decimals are just not good for me. If that's the way you want to go about it, that's fine. This is how I'm going to go about it, okay? I know that 2 times 2 is 4. So 1 over 2 times 1 over 2 is 1 over 4 because you do 1 times 1 and 2 times 2. So what does that mean? That means if I do 1 times 1 times 1 times 1 times 1, 5 times, I get 1 on the top here. If I do 2 times 2, 4, times 2, 8, times 2, 16, times 2, I get 1 over 32. Multiply 1 over 32 by 2, and you get 1 over 16. Since that's negative 2, you get negative 1 over 16, and that's going to be what happens when x is 6. So whatever decimal that is, I don't know. Negative 0.052895314159667. If I'm wrong on that, leave a comment. Rewrite the equation of b, okay, for b, using x minus 1 as an exponent. Okay. I think when I created this problem, I meant to do something else because that's stupid of me to do that. I think I must have meant to do something else. I think I meant to... I'm not going to go back and change it. We will see manipulation of equations later on in this, so I'm not going to lose sleep over that. Easy problem. Easy problem. All right. No calculator. Let's move my face. The population of a bacteria is modeled in the table below. An exponential function can be used to model the data. So I stole this problem off the internet and made a bunch of examples off of it. So day 1, I have 10. Day 2, I have 20. Day 3, I have 40. Day 4, I have 80. Okay, so I can see the exponential part. Every single day, I'm doubling the amount of bacteria that I have. What happens to the bacteria each day? I'm doubling it. Okay, it's like I'm doubling, like we're a city in Ireland. Times 2 for all you layman's out there. How much bacteria existed at the beginning? Okay, well, at the beginning would imply day 0. And if I multiply to get to the next day by 2, then I would divide by 2 to get to the first day, which is day 0, which is 5. 10 divided by 2 is 5. So I started out with 5 at the very beginning. Write an equation to represent this data. Now, what I'm going to do is I'm going to use just a regular old standard equation that looks like this. I did a bad job getting myself in space. So here is what an exponential equation looks like. A times b to the x. okay? Now, B is kind of like the R in the geometric sequence. B is what I'm doing to get from what number to the next. In this case, B is 2. So what I have so far is A times 2 to the x. How do you find A? Well, it would be really nice if I got rid of that 2 to the x. Oh, you know how I can get rid of that 2 to the x? If only x was 0. If x was 0, this would become 2 to the 0. And I know that 2 to the 0 is 1. And so that would just make A all by itself. So if I were to plug in 0 and 5, I would get 5 equals A times 2 to the 0, which means 5 equals A times 1, which means A is 5. So putting it all together, now that we know that, and now that we know that, the equation that we can come up with is y equals 5 2 to the x. So a much faster way of handling this problem, okay, is if we were to start out with y equals ab to the x. B is your common ratio, what you do every time. A is always going to be what happens when x is 0. So find out when x is 0, that's going to be your 5. I just did a little bit of work to get there, just to find out that this is going to be my guy at the end of the day. Okay? So if you're wondering, is this the geometric formula? No, but close, because the geometric formula is set up for you to deal with the first term. This guy is set up for you to deal with the 0th term. And it would make 0 sense that if I gave you, look at all these numbers, 2, 4, 6, 8, you're not going to look at the 0th term for 2, 4, 6, 8 because you're not given the 0th term. So that's the main difference between the two formulas. Arithmetic deals with first term, a sub 1, and geometric deals with the 0th term, regular A. Now that you know, okay, what is the domain of this data? Well, if this is a real life problem, I'm not going to go back in time. So the domain of the data is going to start out at 0, and it's going to go on forever if I choose to do that way. No negatives. It wouldn't make sense. If you were to say plug in negative x, that means, oh, let's go back in time before all of this started. You can't do that. It's ridiculous. Ridiculous. I'm going to use this formula right there to predict the amount of bacteria on day 8. Another fun-filled math equation for me. So I have y equals 5 times 2 to the 8th. Okay. You ready? Some of you might know what 2 to the 8th is. I think it's 256. We'll get there. I'm not sure. 2, 4, 8, 16, 32. 2, 4, 8, 16, 32, 64, 128, 256. 256. I don't know if that's what I said, but 256. 5 times 256. Don't know what that is. So let's do the old-fashioned math route. 5 times 256. I'm doing this kind of the long way, but who cares? You become 30. Drop the 0. You become 25. Drop 2 zeros. You become 10. Add those up, and you get 0, 8, 2, 1. And if I were to keep this pattern going, I would probably get that. At day 6, I would get 320, and at day 7, I would get 640. And so that's a double of 640, so I did it right. So either way you want to do it, I could do it. Moving right along. Let's move my face again. No calculators. Calculators are for the weak. A negative exponent. Yuck. Rewrite this equation in 3 different ways. Okay. I like a challenge. I could write this out in like a affinity different ways. But one of the ways that I can rewrite this out is the 3 is always going to be 3. There's nothing that you can do about it. So way number 1 that we will rewrite this out is let's turn that 4 into 2 squared. Okay, so let's turn that 4 into 2 squared. So f of x equals 3 times 2 squared to the negative x. Okay, now remember a couple problems ago when I said, like, turn it into x minus 1, and I was like, oh, well, that was a dumb mistake by me. I must be meaning to do something later on in the video. Here we are. When you have something in parentheses taken to an exponent, you multiply exponents. So what this final guy is going to look like is f of x equals 3 times 2 to the negative 2x. Okay? So that's one way you can do it. That's one way you can do it. Okay, it didn't tell me how I had to do it. I'm making it up as I go along. Another way, I have a negative exponent. I don't like negative exponents. Usually when you learn in 8th grade math that if you have negative exponents, you move it to the other side of a fraction bar. So you might be looking at this and saying, other side of the fraction bar, there is no fraction bar, so make a fraction bar. So if I wanted to, I can now turn this guy into 3 times, move the exponent, move the whole thing to the other side of the fraction bar and make the exponent positive. So 1 over 4 to the x. And when I put that all together and make it look a little bit prettier, I can do f of x equals 3 over 4 to the x. So that's just another option. Just another option that I can use. What else? What if I decided to, what did I do before? X plus 1, make it x plus 1. I'm going to turn this into x plus 1. Just because, like in this last problem, a couple problems ago, I wanted to do that. X minus 1. Is it already x minus 1? No, it's not already x minus 1. So if I want to do this and make this x minus 1, how can I pull that off? All right, let's find out. If I wanted to make this have the exponent regular x minus 1, first off, I have to use this formula right here. Why don't I make it negative x minus 1? Why not? Okay, why not? I have 4, right, to the negative x. I want to make this negative x minus 1. How can I make this negative x minus 1? We remember from up here that when I have an exponent to an exponent, you multiply the exponents. This would imply that I take a negative exponent and I subtract 1 from it. When you multiply two terms like x cubed times x to the 3rd, you add exponents. So that's going to equal x to the 5th. What I'm going to do here then is I'm going to include a 4 to the negative 1. Now, if I do that, if I do just randomly include a 4 to the negative 1 to this, so that's what I have right there. So that's what I have right there. And this gives me what I want. This gives me the negative x plus negative 1. That gives me the equation that I want to do just for this one example. I'm not allowed to just multiply any number by 4 to the negative 1. So I have to balance that out along this side. So on the right side, if I want to balance out the fact that I multiplied 4 to the negative 1, I have to multiply 4 to the positive 1. So again, I'm just turning this into a very bizarre problem because it says write this equation in 3 different ways. In a previous problem, I had mentioned x minus 1, so I'm doing negative x minus 1. And in order to turn negative x into negative x minus 1, I take the base and multiply it to that base to the negative 1. But I can't just take something and multiply it by 4 to the negative 1. So to balance it out, I multiply it to 4 to the regular 1. Didn't mean to do that. 4 to the regular 1. And that balances things out. So now this gives me the equation f of x equals 4 to the regular 1, or just 4, times 3 times 4 to the negative 1 times 4 to the negative x. 4 times 3 is 12. 4 to the negative 1 times 4 to the negative x means I add these guys and I get 4 to the negative x minus 1. So usually when you have problems that look like this, okay, this is how it's going to usually show up on like a AP test. Very rare. I can't imagine a scenario where the AP people create a problem that say, hey, just create any 3 problems you want and we'll have the graders who grade these things deal with it. No, they'll give you options. And they might be like, hey, look at that guy right there. Which one of these is an example of that? And all of these would be the same exact thing as that. So this comes from, I believe, the 4th, maybe the 3rd section, where it asks you to manipulate exponential stuff. And so that's what we did. That's what we did. Make a table of values. So I'm going to have, let's do -1, 0, 1, 2, 3. The reason why I'm not going to go crazy and make a ton of these is this is exponential, and with the exponential functions, numbers get bigger faster, or in this case, numbers get smaller faster. So I'm going to do a little bit of mental math. Bear with me. Okay. If I want to plug in -1, this becomes 3 times 4 to the negative 1. 3 times 4 to the first is 12. If I were to plug in 0, this guy becomes 3 times 4 to the -0, or 3 times 4 to the 0, which is 3 times 1. If I were to do this guy right here, this becomes 3 times 4 to the -1, which means 3 times 4 to the -1 is 1 over 4. So that becomes 3/4. Sorry, I had to quick pause. My son's watching YouTube really loud upstairs. If I had to plug in 2, that would be the same as 3 times 4 to the -2, which is 3 times 1 over 4 squared, which is 3 times 1/16. Oh, almost my favorite Bible verse. So John 3:16. I didn't do that on purpose. It's just look at God. If I were to do 3... that would be 3 times 1 over 4 to the 3rd, which is 3 times 1 over 64. So 3/64. Okay? And you can see this is why I'm not going to go crazy coming up with a bunch of numbers, because like 3 over 64 is like 0.0 something, like 0.01-ish. 0.02 maybe. That's basically 0. So we know what's going to happen, and this takes us to part C, sketch the function. This is exponential decay. Okay, this is exponential decay. It's actually not exponential decay. You'll see what it is. Speaking too much. Let's plug this in. It actually is exponential decay, because I could rewrite this as, do I have it? How come I never, oh, here's a 4th way that I can write this out. You ready? This is why this is exponential decay. I can write this guy out as 3 times 4 to the -1 times x, which is the same thing as 3 times 1 over 4 to the x. There's a 4th way. So that's why this shows up. Doesn't seem like it's exponential decay at first because of that 4, but it is exponential decay. So I have -1 way up here at 12, boop. And then at 0, 3, which we kind of saw from a previous problem, that when that's 0, that's my y-intercept. So boop. And then when you plug in 1, you get 0.75, so something down here. And when you plug in another one, it's basically 0. And you plug in another one, it's basically 0. And you plug in another one. So what's going to happen is you start way up here, and then you eventually level out at 0. Now, will you ever hit 0? No, because you're just going to keep dividing by 4 every time. Divide by 4, divide by 4, divide by 4, divide by 4. And even if you keep dividing 0.000000 divided by 4, you can always get just a little bit smaller. So what we would say is that the limit as x approaches positive infinity of f of x is going to be 0, which is not that. This is saying, let's go the other way. What's the limit as x approaches negative infinity? Well, if I go to negative infinity, it's going to be super big. Super big. So positive infinity. Yeah. All right, so we have two exponential equations. We have what appears to be a wacky-looking decay problem and a wacky-looking maybe decay. Yeah, it is a decay problem. That's not my issue, though. I don't need to worry about that. All I have to worry about right off the bat is find out what P of 4 is. So P of 4 means let's substitute 4 in for every n. So 4 to the negative 2 times 4 plus 6. Negative 2 times 4 is negative 8. Negative 8 plus 6 is going to be 4 to the negative 2, which is the same thing as, a negative exponent. Let's move it to the bottom and make it positive. And 1 over 4 squared is 1 over 16. See? See it? See it? Now it gets bananas. B-A-N-A-N-A-S. Gwen Stefani. I need to find out when f of n equals p of n. F of n, and I'm going to write it up here, so let's cut things off, and hopefully I have enough space for c. We'll see. F of n is 1 over 64 in parentheses to the n plus 2. Set that equal to P of n, which is 4 to the negative 2n plus 6. Now, in order to solve exponential functions without logs, because we don't know what logs are yet, but in order to solve these without logs, you need to make sure that the bases are the same. They're not. Is there a way that I can write out 1 over 64 to make it look like 4 to the something power? Yes, didn't I just do that? Didn't I just do that like back here? I did. I just erased it. If I have 4 squared is 16, and 4 to the third is 64. So I could write this out as 1 over 64, 1 over 4 to the third to the n plus 2 equals 4 to the negative 2n plus 6. Now, that's not 4, that's 1 over 4. So let's move this guy up and make its exponent negative. Okay, 4 to the negative third to the n plus 2 equals 4 to the negative 2n plus 6. Now, is that 4? No, because it's 4 to the negative third. I need to get rid of that negative third. We already know from a previous problem that if I have an exponent to an exponent, you multiply exponents. But do be careful, because you have to make sure you distribute. So this becomes 4 to the negative 3n minus 6. That's going to equal 4 to the negative 2n plus 6. Now that I have 4 to the blah equals 4 to the blah, I can get rid of those 4s and set those equal to each other. So when you have two numbers of the same base equal to each other, set their exponents equal to each other. Negative 3n minus 6 equals negative 2n plus 6. So let's add 3n to both sides so that I can make this positive n. That'll make my life a whole lot easier. So negative 6 equals positive n plus 6. And one last step is subtract 6. Subtract 6. F of n equals P of n if negative 12 is n. Oh, isn't that fun? I love that. Good old algebra. Good old algebra. And it's worse now. Find f of n over p of n equals 1. So I have to take this guy and divide that guy and set it equal to 1. I got it. A lot of the same rules are going to apply. So let's just set it up and be a little lazy. F of n was 1 over 64 to the n plus 2 over 4 to the negative 2n plus 6. Now, I can simplify something like this. If I have like 4 to the 8th over 4 to the 3rd, when those guys are just 4, when they're the same exact base, you just subtract exponents. So you would get like 4 to the 5th power, right? Well, didn't I just turn that into 4 to the something power? I did. So using the same process, and we're going to wave our hands and pretend that we did everything again, we know that 1 over 64 times n to the n plus 2 is the same thing as 4 to the negative 3n minus 6. So once you have the same bases, you can do a little bit of manipulation. Okay, now that we have a base to the stuff divided by the same base to the stuff, we can subtract those things. So we have 4 to the negative 3n minus 6 minus all of that, negative 2n plus 6. And remember, the goal here is that we need to have it set equal to 1. So this becomes 4 to the negative 3n minus 6 plus 2n minus 6 equals 1. Combine like terms, negative n minus 12 equals 1. Ah, this is a shame. If only that was equals 4 to the something power, then I can do what we did here. Wait a minute. 4 to the 0th power is 1. Oh, I can. And now that I have 4 to the stuff equals 4 to the stuff, then this stuff equals this stuff. And negative n minus 12 equals 0. And then you add 12 and negative n equals 12, and n equals negative 12 once again. Look at that. Oh, it all makes sense. And if you were like, hey, dummy, and that's you talking to me, hey, dummy, couldn't you just have looked at this guy and said, f of n, divide both sides by p of n, and if you divide both sides by p of n, you get f of n over p of n equals 1? You just wasted all this time? Well, yeah, I guess I did. Oh well, it's my video, and more. The longer the video, the more money I get. So I'm hoping that I can make so much money that I can keep my day job and not have to panic all the time. Calculator problem. All right. So what we have is we have ourselves a chart, bunch of numbers, car. The value of a car over its first 4 years is shown in the table. Use exponential regression to model to find an equation for the car's value. So what this concept is called depreciation. When you buy something brand new, it loses its value over time. But it wouldn't make sense. Like if I were to buy a car, it wouldn't make sense for me to be like that. What did I say before? That $100,000 car, it loses its value $25,000 every year, because that implies after 5 years, its value is now negative something, and that doesn't make sense. So maybe it halves every year, or it loses its value by it's now 60% of what it used to be every year, and so you have yourself exponential regression. So what we're going to do is we're going to take a look at this guy. We're going to throw it in our calculator. We're going to answer all of these questions using the process called exponential regression. Okay, exponential regression model. What I'm going to do is I'm actually going to go to Stat Edit, and I'm going to use the exact numbers that they give us. 0, 1, 2, 3, 4. Now, what I'm going to do for the value is so that I don't over confuse myself, I'm going to use the actual numbers. So I'm not going to type out 32. I'm going to type out 32,000. I think that'll be easier to do it now, get that out of the way now and not have to overthink it. 27,000.2 means 200. Okay, 23.1 means 23,100, and I almost screwed that up. 23,100. And then we've got 19,650. And then we've got 16,700. All right. Boom. So let's get out of here. Let's go to Stat, Calc, Exponential Regression, I believe, is all the way down to 0. There you is. And hit Enter. And what I'm going to do is, I know the next two problems that are coming up ahead. I'm going to make sure that I store my regression equation into the y equals part. So I'm going to go to that. I'm going to hit vars. I'm going to go to y vars, function, enter. And now when I have to do parts B and C, it won't be so bad. I don't have to type out so much. Calculate. And there you have it. You can see that A is awfully close to the beginning value of the car, which it is. You know, that's almost $32,000. I have a feeling I'll mention that in a second. There's my B, so let's put it all together. All right, so the equation, as unpleasant as it is, let's do f of x. Maybe I should do this, c of t. C of t, which means the car over t years, is going to equal a times b to the x. A was 31,996.070 times, what was it, 0.849, so 0.850, 0.850 to the t power. Now, this implies that at time equals 0, the value of the car was around $31,000 and 996, blah, 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 which is about right. Okay, it's about right. So this guy is not completely out of the ordinary. So let's see what happens to the car's value, or after how many years will the car's value be $100,000. So before I even set this up, what that implies is the car's value is going to be $100 or $10,000. So $10,000 is going to equal 31,996.070 times 0.950 to the t. Now, what I can do is I can do this two different ways. And I think what I'm going to do, just to make life a little bit easier, is I'm just going to graph that in my calculator, see where those lines intersect, and that should give me the car's value. We'll do that. Be right back. So now what I need to do is I care about finding when this guy is equal to $10,000. So I'm going to go to y equals. I'm going to see that my equation is there, and in my other equation, I'm going to set it equal to $10,000. Now, what I could have done here is I could have subtracted 10,000 from this whole thing and found a 0, but I'm just going to find out where these two intersect. When I hit graph, I don't expect to see anything. Why? Because all the action is happening way up here. So if I wanted to see something, maybe I'll change my window to, I don't know, the X max or Y max rather was, what was it, a $32,000 car? So let's bump it up to $33,000. Okay? Hit graph. And we can see that the value of the car starts out way up here, and then over time, after a year, here it is. And after 2 years, there it is. That red line represents when the value of my car is going to be $10,000. So I need to find out where these two lines intersect. So I'm going to hit second, trace, it takes me to calc, and I'm going to go to intersect. The fun thing about intersect is all you have to do is hit enter, 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 boom, boom, boom. And there you have an intersection of 7.1536, so we'll round that up accordingly. Before I even move on, I think that is an 8. I think when I drew it out, I made it look like a 9, so maybe I accidentally said it was a 9, but it's an 8. So I'm going to go back and fix that. After typing that all in my calculator, the t that I ended up getting was 7.156. So 7.156 years. So like February? I don't know. Maybe March? Now this is the same exact type of problem. When will the car be half of its original value? When? So same exact thing, but I know that the original value of the car was $32,000. So somewhere after year 4, I'm going to hit $16,000, and that's going to be 31996.070 times 0.850 to the t, and we'll do the same exact thing that we did in part B for part C. So let's do it again. And we're going to use, what number? Half of it. So that's 16000. If I hit graph, the only thing that's going to change is that red line. And now we do the same exact thing. We need to find out where they intercept. So second, calc, intersect, 5, enter, enter, enter. We have 4.262 stuff, so we'll round that up accordingly. All right, so the time for this one is a little after 4, so 4.264 years, which makes that makes sense. Because after 4 years, we were at $16,700. So if I wanted just a flat $16,000, it's probably going to be at some point after 4 years. So, yeah, there you have it. Depreciation. All right. A father complained. Oh, those dads always be complaining. Oh, a calculator. A father complained that his son's allowance of $5 per week was too much. His son replied, "Okay, Dad, how about this? You give me a penny for the first day of the month, 2 cents for the second, 4 cents for the next, 8 cents for the next, and then every day and so on and so forth until you're done." And the dad's like, "Oh, I can do this. I like this. This is fun." Okay, you asked for it, Dad. You asked for it. Write an equation for this scenario. What I'm going to do is I'm going to make a small table. And we're going to do X and Y. And on day 1, you gave that kid, what was it? A penny. And then let's double it. And then 4 cents the next, 8 cents the next. So let's pretend I didn't say double it. Let's pretend that I have no clue what's going on. Although I do know it's exponential. But let's just write that out. Yeah. 8 cents for the next. And every day for the rest of the month, find an equation for this scenario. We're going to use exponential regression again. So let's run to our calculator and see what happens. All right, so let's see where this little brat, how much he's going to make money. Let's come up with an equation. We started out with a table. We made our own table, so let's just use that. We have day 1, day 2, day 3, day 4. Day 1, he had a penny. Day 2, he had 2 cents. Day 3 is now 4 cents. And day 4 is now 8 cents. Does that make sense? Hee hee. Now let's find out our equation. Let's quit out second mode, stat, Exponential regression, if you go over to calc was 0, so let's just double check. Yes. Enter, 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 enter. And there you have it. There's our formula. Okay, so the equation that we got was y equals a 0.005 times 2 to the x power. How much will his son get on day 31? Let's find out. Now, what I forgot to do in the previous problem is I forgot to store this formula into y equals, so let me remind you how to do that. We have to go through the whole process again of regression. So calc 0 is exponential regression, but when I store my regression equation, I'm going to go to vars, y vars, and store it into y1. Okay, so when I hit calculate, I get the same exact function that I had before, but now when I hit y equals, there it is. It's just, God forbid, it gives you 0.005. It has to do all of that. So thank you, TI-84 Plus. You guys are great. We care about what happens on day 31. It can't be that bad. I mean, you're only getting a penny to start out with. It can't be that bad. Let's go to table by hitting second graph. And at day 0, that doesn't matter. But day 1, you have a penny. And day 2, you have 2 cents. We knew that would happen. Let's just keep going. Let's keep going. Day 10. Oh, great. We owe him $5. Yippee. Uh-oh. Oh, boy. Oh, no. Oh, no, no, no. No, no, no. Why are kids so freaking expensive? Look at that. Holy cow. That's $10 million. I don't have that kind of money. I'm not PewDiePie over here. Oh, let's write that down. Oh, that turd. He tricked us. He tricked us to the tune of $10 million. Holy cow. $10,777,418. And let's not forget the 24 cents. Oh, I hate kids. I hate them so. Actually, I love kids. I have 4 of them. Rewrite the equation if the son started out with 5 cents, doubled his money every third day, and owed his dad $45. So, all right, so now what I have to do is rewrite the equation if the son started out with 5 cents, doubled his money every third day, and owed his dad $45. Let's not worry about the $45 until the very end. You'll see why in a second. On day 1, 5 cents. Every third day, which means day 4, it's doubled. And then day 7, it's now 20 cents, so 0.2. I don't know why I wrote it out like that. And on day 10, it is now 0.4. So let's type that information into our calculator and see what we get, and then we'll deal with that $45 in a second. All right, last but not least, let's do the same thing but with new values. Okay, so let's go to stat, edit. Don't know why I went over to calc there. And let's type our values in. We have day 1, and then 3 days after that, and then 3 days after that, and then 3 days after that. Every 3 days, stuff happens. Okay, we start out with 5 cents, so that's 0.05. Enter. And that's 0.1. Enter. That's 0.2. Enter. And that's 0.4. Enter. Let's go to second. Quit. Stat. Calc. 0 it was, right? 0. I don't need to store this. I just need to do this and write this out. Okay, so this equation is much, much, much worse. Y equals 0.3968, so 397 to the 1.259, so 1.25, actually 60. That's what we're going to have to do, to the x power. Oh, he owed his dad $45? Minus 45. That's it. 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 And we're done. Thanks for watching. This covers everything from the first 4 sections of chapter unit 2, whatever you want to call it. So, I'm getting a lot of requests to make more and more and more of these videos. So that's just what I'm going to do. So please be patient. This is the first year that anyone's doing AP Pre-calculus. So, but thank you guys for watching. I hope you enjoyed it. I hope it helps. Let me know if it does, because the comments, the few comments that I get are like, this really helps, I love you. That's what keeps me going. That and the sweet money that I make from my YouTube, which is barely nothing. Bye.